bit more sugar.
All right. Okay, so we'll have the test Thursday to be in class. I guess do the best you can. If I find that everyone struggled, I'll figure something out.
Typical platform, bring notes and books.
Yeah, open book, open notes. I'm going to go through, we're going to go through everything that's going to be on it. We'll go through probably 3 to 4 practice problems, and maybe I'll try to find some more problems to do for you to post, okay? So it's going to cover fluid kinematics, and linear momentum. So homework 1 and 2, pretty much. And I haven't made it yet, but I'm thinking maybe a couple like multiple choice, like there was on the homework 1 where you had to find vorticity, and maybe a couple short answer, and then 1 or 2 not full engineering problems, maybe mini short. They're a little bit longer than short ones, just to make sure you understand the concept. Okay, so let's go through fluid kinematics. Oh, and I do have your graded homework. Let me pass that back right now before I forget. So if you want to fix some of the stuff, please go ahead and do that. Can I give you 2? Okay. All right. Okay, so fluid kinematics. In this, I'm going to give you a velocity profile. Okay. So for example, say I give you this. So we'll cover every kind of the basics, and then we'll do some practice problems. So if you remember, this is whatever's in front of the I is what for velocity? U, yep. So this is U, and what's in front of the J? V, yep. So this is 2D. And just as a side note, how do you find the magnitude of V? Just U squared plus little v squared. You wear glasses, Listen? No? What was that? No, I don't. I like it. Give me an attitude. I like it. I don't know if you did, but I liked it. Okay, now how do we find acceleration? You remember? I guarantee there's one. I'm going to put something like this on the test. I'm going to say, okay, find the acceleration. How many accelerations? There's going to be that. Well, it is, but then we blow it out, right?
Yeah.
It's 2D, right? Mm-hmm. So you're going to have how many accelerations, technically? 2. You'd have AX and AY. And if you remember, and I think I have a practice problem that deals with time, so you can see that. Oops, that's not T, that's X. So those are partial derivatives. Partial of u with respect to t plus u times the partial u with respect to x plus v partial u with respect to y and so forth. So if you notice, a lot of the stuff in the fluid kinematics is have your book open or write all those equations down from lecture notes and the videos that I posted. Really, they're all what? They're all derivatives. They're all partials. So as long as you have the equations, you can at least get a lot of the points, because then you can try it and mess up some of the math. That's fine. Okay, so in this problem that we have right here, is the velocity a function of time at all? No. So that term would be gone, right? We have u, and there is a u with respect to x, so we're going to keep that. And there is this term too, right? Because there's a v and a part of u that's respect to y. Okay, but there's no w, so that term would go away. So let's just write this so you have it. So u was negative 5x plus 4y. And then the partial of u with respect to x, what is that? Negative 5. Yep. And then this u is here. So you know, okay, that's where I found it. And then plus v, which is negative 10x plus 2y. And then we're taking the partial of u with respect to y, which is 4. Okay, does that make sense? So then we could just plug in the values, like I would tell you, find the acceleration at x of 1 and y of negative 10, you just plug them in. Okay, this would be the ax, and then the ay, you would then do the same thing, but all these u's would be changed to v's. Okay, so definitely going to be probably a multiple choice like this. Find the acceleration. Maybe I may say find a y instead. Just make sure you have those equations in front of you. All right. Good. Next is kind of like flow patterns and flow viz. Visualization. So there's streamlines. Stream tubes. There's path lines. Streak lines. Timelines. Profile plots. Vector plots, contour plots.
Blame Mr. Bass. Yeah, cross your fingers.
So, streamlines. Well, if I have an object like this, and say the wind is blowing that way, what's the streamline look like? Well, they kind of tell you the flow pattern, what's happening, right? Something like that. So streamlines, and if you remember, you had to find the streamline. Remember that in the homework? In order to do that, you have to remember this equation. I don't like that streamline, that one's bad. Let's fix it like this. So look at whatever problem you did I just gave back where you had to figure out the streamlines. Okay? If I do that, it'll be something easy that you can integrate or take the derivative of, okay? All right, so you use this equation right here and say you just plug in what u is and you plug in what v is and then you integrate. Okay, I'd probably give you something easy that where this could probably go up top and then it's doable, okay? All right, and when you find the streamline, what does that mean when you're finding the streamline? That means you're solving for y as a function of x, okay? So when you do this, you actually solve for y on the left and x is on the right. Okay? Questions on that? There won't be anything like log identities, nothing like that. So it's going to be something doable where you can do that with no I mean, if you're stuck, I'll make sure to help, but it should be fine. Okay, so that's streamlines. Stream tubes, all that is just a collection of streamlines. Okay, I won't really do anything with that. Now these path lines, streak lines, and streamlines, let me show you this real quick. I don't know where I should point this.
There's that little
Okay. Okay. So here is I know they can't see it, but that's fine. On this side, these red ones, or whatever black looks like, those are streamlines. Okay? Streamlines, remember, are always perpendicular to the velocity vectors. Okay? This black is what they call a path line. Okay? It's a path that a particle that would take as time goes on. So this right here is for unsteady flow, meaning that the flow could change in 1 second to the next second to the next second. Okay? You see these dots here? Those are streak lines. So what I did is at injection 1, if I scroll down here, I injected it at time 0 all the way to the left, and it got to that point at 2 seconds. Number 2, I injected it 0.1 seconds after I injected the first one there, and it ended up being there. And then 3 and 4, all the way, like every 0.1 seconds I inject it, then I draw a line and I connect it. That's what a streak line is. Okay? All right? So you have streamlines, path lines, and streak lines. For you, just to kind of remember, a streak line is typically what you see in a wind tunnel. Like that heavy flow, that heavy fluid, it's heavier than air. Okay, that's what you're seeing. You're seeing a streak line. Okay? Which are very, very close to streamlines, but they're gonna have more inertia, and they won't be able to follow the object in the back as much. Okay? So just remember, streamlines are very important. They just give you the fluid flow over an object. And remember, streak lines are used typically for flow visualization of wind tunnels because it's a heavier fluid. All right. I'm going to switch back and we'll continue. All right, so that covers some of that. Timelines, those are just are used when you have like a plot of velocity versus time if you're looking down some section, so don't worry about that. And then these last two, vector and contour, oops, sorry. Oh, it kicked me right out when I did that. Display, connect. There. So vector plots just show you vectors, okay? And they're pretty much used if you want to know if there is flow separation, okay? If you're looking and you want to identify if there's flow separation, a vector plot would be best. What are contour plots typically used for? Remember in the homework?
Would be like
Temperature, which is a scalar. Yep.
Okay.
Yep. So anytime you need a scalar, like speed, which is scalar of velocity, you could use contour plot. Okay. So there could be some multiple choice where, kind of like one of the homework problems you had, what should be best? Temperature would be for contour and so forth. Okay. So a lot of this stuff is looking at something and identifying, okay, what is it? All right. So that covers that. Vector. Okay, we'll go through that in a second. Okay, now there's also types of motion, which I didn't cover in class, but I had a video on. Oops. So there's rate of translation, rate of rotation, there's a linear strain rate, volumetric strain rate, and shear strain rate. Oh, and we'll do one more, vorticity. And as this one, if this vorticity is 0, then there's no rotation. Does anybody have their book on them? No? What's that? Did you? Say, basically every one of these oops. Every one of these will have an equation that you can look up in the book. And the video that I had has the equation that you can just use. Okay? All right, they're partial derivatives. As long as you have them, you should be able to know and how to do it. It's just a partial derivative. All right? And the rate of translation is just your velocity. So that's already given. So if I tell you v and I say find the rate of translation, that's all it is. It's just v. And then every one of these is an equation that you can use in your book to figure out if it's spinning. This linear strain rate means does it stretch in the x or in the y? Okay. Volumetric strain rate is does it actually like expand out in all directions? And if it does that, that means it's compressible. So it could either expand all the way out or compress in. And then shear strain rate is, so if the corners pinch, okay, that's like a shearing force. So there's equations for that. And then vorticity talks about what? You have homework problems on that, if it's spinning around. Okay? And you had that equation for that. Give me a second. I do want to show you these equations. So I will find them. Online books. It's actually really nice. I don't have a page number, so bear with me. Chapter 2 is probably, let's try 90. Oh, more than that, 20. Oops, did it work? Almost. Froze. Oh, great, now it doesn't want to work. Come on. Never takes this long. Chapter 5 still. While this is working, do you have any questions? Ah, it's really slow. There's going to be probably some multiple choice, some short answer, and probably won't be any full engineering problems. There'll be like mini engineering problems. It's more of, okay, make sure you understand the concept. Come on, this is ridiculous. Is your internet that slow? No? It's never this slow. There we go. Getting warmer. There's no sense of writing all the equations down because it would just take, could have, but. There we go, getting warmer. Next page, we'll have the first one. Right here. So here is the rate of rotation. Actually, let's go to this one. Right here. So this equation, either you mark it in your book or just write that down in your cheat sheet. And if you notice, they're partials. Like here is W with respect to Y, V with respect to Z. Okay. I'm not expecting you to know how to get to this. That's way out. There's no need for it. As long as you understand, here's a velocity profile. Tell me if this thing's rotating. All right. Now, if you remember, what was vorticity? Was this divided by 2? Okay. So your angular velocity divided by 2 is really vorticity. What they did is they avoided this 1/2. That's all they wanted. They kind of just said, all right, don't worry about it. Are you writing it down? Oops.
So you won't have to worry so much about the strain.
I'll give you those. I'll have you write those down too. It's actually better when I didn't zoom in, huh? There. So that's a rate of rotation. And actually, up here is a really cool little picture. See this top left, A? That is your rate of translation. That means velocity. What's the unit of velocity? Meters. So how many meters did it move in a second? This right here is rate of rotation. Does it rotate? This block of fluid. This is your linear strain rate. Does it stretch in X? Does it just stretch in the Y? And then here is where it pinches because you got a shearing effect. That is your rate of shear strain rate. Okay. All right. Did everyone get that one?
So the rotation in radians.
Just writing the, which one you writing down?
You write down that littler one, did you?
Yeah. Yep. This, if you notice, is just for 2D. No. I have my book if you need to get those too for the test. You're good? Everyone good now? Okay, so down here is your linear strain rate. So this is epsilon XX. Okay, epsilon YY and ZZ. So it's just du dx, dv dy, and dw dz. It just tells you, does it stretch in those directions? And the video goes through, if you watch that video, it'll go through a whole example of all this. Okay, so you can understand partial. It's on Blackboard, yep. It's actually a review of streamlines and then talks about these. Yep. And then what do we have left? We'll have volumetric and shear. All right, let me go to the next page because the next page should have right there. So what I would write down is just write volumetric strain rate and set it equal to epsilon XX plus YY plus ZZ. Okay. So all this stuff at the beginning, don't even worry about it. Just say volumetric strain rate equals this plus that plus that. So the volumetric strain rate if, say, epsilon xx, so it stretches in the x direction, say that was -2. Okay, actually didn't stretch, so make it 2. Okay, stretches in the x2. In order for it to be incompressible, what do you think the y has to be? Or equal to, but opposite sign. So it'd have to shrink -2. So in this case, in order for it to be incompressible, meaning this can't, it's not compressible, this type of fluid, like this would be 2, that would have to be -2, meaning it shrunk. Okay? All right, in order to stay the same amount of volume. Okay? Good. So that's that, and then I think the next page is your, don't even write that, just write those if you want, those 3. Okay? So that tells you if the corners, because they're shear, are stretching. And if you notice, it's partial u with respect to y and v with respect to x, meaning it's corners, not just the faces of x. Okay, looks like everyone has it. So let's do an example. So this was given on a test before. So V is x squared I plus, uh-oh, did it kick me off? It's weird that it does that. It does it a lot sometimes. Yeah. Yep. Okay, so here is the velocity profile. And first it wanted to tell me, find the stagnation. Do you remember how to do that? Yeah. So U is set to 0 and V is set to 0. So what's the point? Stagnation. 0, 0. Yeah, there's no other point it could be. The stagnation point is at 0, 0. Okay, next one was find AX, which is du dt plus v du dx plus v du dy, right? So what can go to 0? Yep. And? Yep. Because du dy, there is no y in u. Okay, there is no y here, because u is x squared. So all we have is x squared times what's the partial of u with respect to x? So 2x cubed. Okay, then it wanted to find a y, and that's dv dt plus u dv dx plus v dv dy. And again, what 2 can cancel? You get there? Is there a t in v? No. Is there a x in v? No. So we get v, which is y squared, and the partial is 2i. 2i cubed. So the next thing is I told the students I wanted them to plot maybe 3 vector plots, 3 or 4, by hand. Okay, so let me show you how to do that. It's not really that hard. So what we want to do is we want to pick values of x, y, u, v, the angle, and say the magnitude of big V. So this is little v, and this is the magnitude of big V. And on the left here, we'll do a plot. We'll call this y, and we'll call it x. Oh, what points do you want to pick first? Let's do 1 and 1. What's the value of u? I think it's 1 squared. So remember u is x squared. We plug in 1, we get 1. Yep. So the value of u at that value is 1. What about v? Is 1. Okay. The angle is tan to the minus 1 of little v over u. All right. I'll show you that in a second. So the angle is 45 for the first one. And the magnitude of v is u squared plus v squared, which is radical 2. So let's plot this first one. Where is it located? Right here. At what angle from the horizontal? 45. Boom. Actually, you know what I'm going to do? Make it nice, like this. There. If I break this vector up into x and y, You don't have to draw this. I just want to show you. That's U, and that's V, right? Do you see how that is the angle? We take the tan of those two. Okay. All right. Let's do the next one. What would I pick? Let's pick 4 for X and 1 for Y. So what's U? 16. And V is 1. The angle is actually 3.58. And we get radical 17. So this one is over here to the right. Why?
What's 16 squared? Plus 1. 16 squared.
Do it in your calculator? Is it not right? Do you have a calculator?
Yeah. Did I do that wrong?
Yeah, so I don't think you squared 16. I think you just added it together. You did 7.
Oh, yeah. Yeah, I just added them. So what does that come out to be? 4.12? Okay. Now what's the square root of 2? Not right, I checked it. I checked the square root of 17, it wasn't right. 1.41, okay. Yeah, I just added them. I don't know why I did that. Is it 4.12? Square root of 17? What did I do, Garrett? Did I get the right answer?
16 squared plus 1 squared is 16.03. That.
I don't know. Okay. 16.
Yeah, that's what I meant.
So what do we?
16.03.
16. Okay. Okay. Yeah. Okay. So this.
I read it.
I read it wrong. Okay. Sorry. 16 point what?
That was 03.
03. Okay.
The magnitude of those two numbers would have to be between them, right?
Yeah. Yeah. I don't know. Yeah. Yeah. See, sometimes you mess up the easy stuff. So that should be at 4.1. And the angle. Can you check the angle for me? Just make sure I did that one right. That's right? Okay. All right. So we got the magnitude, we got the angle. So we're at 4.1. So when we draw this, it's pretty much going to be like that, right? And it should be how many times bigger than the other one? 16, okay? Now, when you do this, if I have you do it, just make sure like, okay, this is definitely going to be longer than that and at a smaller angle, okay? But that's how you do that. Does that make sense? I wouldn't have you, I'd probably have you do 3. I'd probably tell you, do maybe 1.1, 4.1, and 1.4. So get an idea, okay? But that's how you do that. That makes sense, right? All right. Other questions? Okay, so here's another one. And oh. Okay, give me I want to scan this on here. So actually that's a good idea. Okay. So here is another fluid kinematics question. Kick me off. Figures. 5-minute break. Work fine. Come on. No, it doesn't want to work. All right. So here is, they actually gave you the speed from this starting location to the right in an exhaust pipe. Okay. So it's governed by this equation here. And I'm going to write it like this. All right. So they give you V naught, which is 8 feet per second. They give you these constants A, B, and omega. And they want you to calculate the acceleration for a few points. Okay. If you looked at this problem, what would you do first? Would you be like, oh my God, I don't know what to do? MATLAB. You could MATLAB it, but really what I just told the students to do is I just wanted to find AX. Why is it AX? It's only in the x direction. So this velocity then really is what? Or U. Yep. So if you were to plot this, what would it look like, roughly? The velocity inside from this starting point to the right before it exits the exhaust. Well, it has a sine wave in it, right? So it should be wavy like that. Yep. Yep, it could be higher initially to the left and maybe flat on the right side. Yep. So this is like an applied problem, right? They give you this velocity profile on this pipe, and you want to find accelerations, which really do what in the end? You can find forces. So that's why you need to do this. So once you know accelerations in here, you can use that to find your force. Okay. How do I find AX? We're dealing with fluid kinematics. What was that equation? This one. I think this is the third time I've written it today. What's the main difference this time?
Get rid of the except for X.
And
T.
and T. So what you have to do now is you have to take the partial of this equation with respect to T. What's that become? Oh, I believe it's, I think it's still V naught AE to the negative BX times omega, right? Times cosine omega T. There's no negative? Not for the derivative from sine to cosine. So V naught AE, yep. Now, we already know what U is, right, for this term. Let's find du dx. What's that? Well, it should be V naught sine omega t, because those are all constants. They come out. And the A. And you remember how to find the derivative of that? It's the same, e to the negative bx times a negative b. I won't put that dot in there because it confuses you. Negative b. Okay? Was that bad? No, but looking at it initially, oh my God, what do I got to do? Really, you just take the partial of u respect to t, which we did, and then when we take the partial of u respect to x, everything you treat everything else is constants, but the x term. And the derivative of this is just itself times whatever's in front there. Then you plug everything back in. All I wanted the students to do was to break it down into these terms. That's all I wanted them to do. Okay? But now you've seen one where you have time in it, and it's doable. Okay? And this is common. This is what sometimes they do. Oh yeah, E-terms are really easy. Yep. All right, questions? Okay, so that's pretty much, I've given you everything that you possibly would need to know for fluid kinematics. Okay? The second part of the test is going to be linear momentum, and you're working on that problem now, which is kind of fresh in your mind, right? Hopefully, you're working on it. So linear momentum, what's the equation that I want you to write down? Keep going. So you have MA plus V, and then I know there's, which one's, first one's in or out? Out and in. I will not test you on the last question. I won't do the moment ones. That'll be later. Okay. After the test, we're going to cover more of that and relative and angular stuff. Okay. This is only going to focus on this. So first, 4 problems? If you know how to do those, you're going to be golden. And I'm going to do another problem here with the jet ski. Okay. So what are all the forces on the left that you need to write on your free body diagram? Okay, so there's pressure forces, yep. So P times A. You also have weight. Yep. I'll put parentheses. Reaction forces. And those are what, really? Those are due to really the stuff on the right. Okay, but reaction forces. Yep. Pressure, weight, and reaction forces. There's nothing else. I mean, there is shear forces, but we kind of neglect those. We don't worry too much about those. Okay, but there's pressure, there's weight, and reaction forces. This stuff on the right, this is all what? Fluid forces. So you're going to label where the fluid comes in and where it goes out. And what's the other important conservation equation you should be using? Conservation of mass. So remember conservation of mass. That states summation of m dot in equals the summation of m dot out. And what do you think the MA term is going to be for your case? 0, because we haven't dealt with anything moving yet. So that's going to be 0 for you guys. But write the whole thing out and cancel it. Okay. Make sure you know how to do the homework problems, because there'll probably be one like that on the test. Here is a jet ski problem. So here's some water, and here's the jet ski. What's that? Actually, it's not a jet ski, it's a personal watercraft, right? Because a jet ski is the actual brand name, right? But everyone says it, I think. Come on, I clicked the arrow. So the water comes in right there into the jet ski at 30 degrees. We're at some angle, okay? So the water's coming in at 30 degrees to the jet ski. Okay? And then it shoots out nice and straight back here. Yep, yep. Okay, and we create, well, let's make this purple. Purple is thrust, and we're going to call it Rx, and it's 300 pounds. Already here in 5 minutes. Okay, it's fine. So I'll give you more problems too later. So the first thing, what would you do to set this up? We're going to assume that it's moving, even though it's moving at constant speed. So your MA term is going to be 0. Okay. So here, we want to do is our control volume. All right. And actually, let me fix this. Let me redraw it for you. A box. I didn't mean to do that. Come on. It doesn't want to erase. So down here, let's pick a control volume. So I made boxes, and it's coming in here at 1, and it leaves here at 2. What's that? That's what actually the question is asking, what's the volumetric flow rate? Yep. Yep. And I think it gave you, did it give you something else? It gave you areas. Yep. But I just wanted you to set it up. I just want to make sure you know how to set this up. So that's our control volume. And we have this thrust generated, which we'll call Rx. So over here, if we sum the forces in the x, MAX plus, what was it, out first, minus summation of m dot v x n. So he's moving at constant speed, so that term is 0. So anytime it's constant speed, or if it's stationary, okay, so I could give you one of those two, it's going to be 0. Forces on the left are reaction, so we have Rx. In the x direction, and then over here, what is coming out? There's 2, right? The state 2 of the control volume. So we have m dot 2 times V2. And what's coming in the X? Yep, times V1X. So Rx equals m dot 2 V2 minus m dot 1 times, well, I believe it's V1 cosine theta. Questions so far? Does it make sense? Slightly different than we've done before, but it's the same process, right? You pick your control volume. I just picked a box, solid box. You know this is coming in at 30 degrees, shoots out straight. And down here, based on conservation of mass, m dot 1 equals what? M dot 2. So Rx equals m dot V2 minus V1 cosine theta. So far, make sense? All right. Now, there is something that you can do, is you can state that m dot 1 equals m dot 2, like we said. This is rho A1 V1 equals rho A2 V2. And what I can do is I can solve for V2 in terms of the areas and V1. And technically, you could plug this back into here and have kind of a more simplified equation. Where if I give you the areas of the two, you can then kind of go further. I just wanted to show you that in case you had to do that, okay? What is that? The outside or inside? In the room? Okay. Yep. So, questions with this? So, I'll post 2 or 3 more problems of this stuff with solutions so you can look at them. We did a lot with the fluid kinematic because I figured that was kind of out of your mind, but now hopefully it's back in your mind. Make sure you know how to do all the problems in the homework, know how to understand this problem, and I'll post 2 or 3 more problems. Okay? So come prepared for Thursday, and if you have questions, I'll be around, all right? Okay. All righty. Thank you.